welcome once again to RF transceiver design course. We are discussing the mixer design. In the last class, we have seen the active mixer. For active mixer configuration, how the flicker noise and thermal noise can be calculated, and how what are the ways we can try to improve our mixer circuits to reduce the effect of linearity, non-linearity, and noise. Now we will discuss about the means passive mixer, which is widely used in RF circuits. So if we consider the active mixer here, so the in active mixer what will happen, that same thing what we are doing, the first is a voltage to current conversion, and then again this current is switched, and that current again is converted to voltage. But what will happen, that during this entire conversion process, the current I is going to remain in the active uh, circuits, and that current will significantly add the flicker noise, and it will also increase the power consumption. Now if we consider another configuration, that is, if we take DC out, only consider AC that we want to switch. First we convert the voltage to current by using amplifier, and that current means DC we can block, and that AC current will be switched by the LO, and that again will be current will be converted into the voltage. So this is how the passive mixer that we can design. Now the advantage, so here what same thing has been written. So passive mixers rely on a power efficient on off switching. So this switch should have a efficient, this switching should require a high LO power, and that should be efficient. So that is why we need to have a sharp rail to rail waveform are needed for improved performance and increasing the what will happen, that effectively it increase the power consumption in LO delivery circuit compared to the active mixer. However, in active mixer you do not require that much LO power, in passive you require a high LO power. However, we can have an advantage. What is the drawback of active mixer? It has a linearity constraint due to the device stacking, because there are multiple devices at the input side and then at this LO and again conversion. So this minimum 3 stacking of the device, and that will, we do not have a sufficient overdrive, and that will reduce the linearity, and as discussed it has a very poor 1/f noise. So in passive mixer, cascading the stages resolve this issue whatever is the drawback in active, and can include a blocking capacitor for 0 DC bias and reduce the flicker noise. The fundamental difference between the active and passive mixer is that the latter commutes the AC signal, whether it is a current or voltage, but it uses the AC signal as we discussed. And you can also remove the blocking capacitor by considering the better common mode feedback circuitry for equalizing the DC levels on the both side of the switch, and it will also eliminate the DC current. So this is how the passive mixer can be evolved. So there are two kinds of passive mixer, one is a current mode passive mixer and another is a voltage mode passive mixer. So in current mode passive mixer, a trans impedance amplifier is essential for converting input current to the voltage and providing a low input impedance to the mixer switches. And in voltage mode passive mixer, the buffer following the mixer should present a high impedance circuit. So you need to have a buffer following the mixer, high impedance circuit to ensure a voltage mode operation. So, we can consider it as a current mode and a voltage mode passive mixer. So, mostly current mode is widely used passive mixer. So, in current mode mixer, now what will happen, that how the LO, because there are a LO signal which will have a different duty cycle, how the LO duty cycle will impact the overall performance of the passive mixer. So, if there is some overlap of the clocks, so operation with the overlapping clocks, if we want to understand. So, during the period of T by 2 less than T, T by 2 plus tau. So, this is a tau, and this is a effective LO 2 and LO 1. So, when both the switches turn on, so during this period what will happen, that both the switch will get turned on, and what will be the result? The RF current is a split equally appears at both the output branch. It will have a it will appear at the both the output branch, and if it consider the differential measurement, there is a result of no net output current. So, what will happen, that during the negative, so there is a two kind of overlap, one is a negative overlap and another is a positive overlap. So, here the in this case this tau is this LO2 is appearing after certain period of time of the tau, that is a negative overlap, and if there is a positive signal, that LO1 is appearing after certain period of time, that is a tau, that is a positive overlap. So, what will happen here, that during this period of time the current means differential, if you consider the differential measurement, the output is 0. So, your effective conversion gain will reduce. We will try to analyze. So, if operation with a non overlapping LO signal, in the case of non overlapping LO signal, there is a negative overlap time duration tau, where both switches are off. Result, no current appears at the output during this duration. So, here this during the negative overlap, this switch, both switch will be off and there is a no current, and during the positive overlap both will be on, but because there is a differential we are considering the differential measurement, then there is a 0 current. Effectively your output will remain same. So, your output current calculation, if we want to calculate the output current, is equal to the source RF current Is multiplied by the effective LO waveform. So, this is our effective LO, this is LO1, this is LO2 and this is our effective LO. So, the output current IO is equal to the source RF current Is multiplied by the effective LO waveform. So, this is a cos omega LO tau by 2 into sin omega LO minus omega LO tau by 2. So, the effective LO signal fundamental frequency is determined by a simple Fourier analysis and we can write it in this form. If we consider the multiplication of these two, the mixture conversion gain we can write it down in AI, which is equal to 2 by pi cos omega LO tau by 2. So, now the conversion gain is depend upon the duty cycle, means that tau, how much overlap is there. So, if there is a no overlap, this will be eliminated if you consider tau is equal to 0. But if there is a overlap, then you will have a different your conversion gain will reduce. So, here your AI is a maximum when tau is 0 and indicating a 0 overlap, or for 50% duty cycle for the LO signal. So, there is a two possibility. We can either have a 50% duty cycle or a tau which is a 0. So, in that case there is a no overlap and we will have a 50% duty cycle. So, there is a deviation from 50% duty cycle result in either a no RF current output. So, here there is a one more approach that we can use, that is a quadrature mixer and LO signal overlap. So, quadrature mixer in LO waveform in quadrature mixer has a, so that is shown in the figure. So, in quadrature mixer what we will consider is a, we apply the LO signal 0 and 90° phase shift, and that 90° phase shift will help us, because we have already seen that if we want to reduce the image component in the our signal, incoming signal, that image component can be reduced. There is a possibility there are a self image also, and there is a image exists due to the LO frequency choose either high or low side LO injection. So, that can be we can able to reduce the image by using a quadrature mixer. So, what is the LO waveform in quadrature mixer? LO waveform is shown in figures are shifted by t by 4 or pi by 2. So, it is a 90° phase shift, and LO 1 and 3 represent differential LO signals, and while LO 2 and 4 represent the differential Q LO signal. So, here LO 1 and LO 3, LO 1 and LO 3, if we consider this, LO 1 and LO 3 represent the differential LO signal, while LO 2 and LO 4 represent the differential I signal. So, LO I signal, that is in phase, and LO 2 and 4 is a quadrature differential signal. So, effect of negative overlap in that where tau is less than 0. So, for negative overlap result in a period where all 4 switches are off. So, we say same thing what we have considered, and mixer conversion gain is expected to decrease in this case. But for in the positive overlap, when tau is less than t by 4, only LO 1 is active and directing RF current to TIA, and for t equal to t by 4 to t is equal to t by 4 plus tau, both I plus and Q plus switches are active and splitting RF current. So, at t is equal to t by 4 plus tau, then I switch turn off and no current appears at the output. A similar situation occurs for the I branch, and we will get the Fourier series analysis results in a fundamental LO signal. So, this is what we will get if we consider the positive overlap, that is a 2 root 2 by pi, that is a cos omega LO tau by 2 and cos omega LO minus omega LO tau by 2 minus pi by 4. So, this is how this is a ideal LO waveform. So, there are LO 1, LO 2, LO 3 and LO 4. So, you can consider that LO 1 and LO 2 there is a no overlap, means LO 1, LO 2, LO 3, LO 4 there is a no overlap. This is the ideal waveform, and this is the overlapping LO signal. So, if this is the ideal, what will happen, that your signal effective LO signal will look something like this for this complete T cycle. Now, if there is a overlap with the tau, and that will result in a signal which has a configuration like this. So, here this is a practical LO signal and this is a ideal LO signal, and when we try to consider the LO signal, we will try to make a non overlapping cycle, and if we try to plot the conversion gain versus the duty cycle. So, in this case conversion gain versus duty cycle, if we consider only in phase component or if we consider I and Q both. So, if there is a in phase I, the maximum gain will get around 45 to 50 percentage of duty cycle, that is a 2 by pi. But if we have the, if we consider the IQ case, if we consider this analysis for positive overlap, and if we have in phase and quadrature component, and that this graph is plotted for 40 nanometer technology switch, and this has a, so the technology that is used is a 40 nanometer passive mixers, and that will give the maximum gain of root 2 by pi at 25% duty cycle. So, if the duty cycle is at 25%, in IQ case you will get a maximum gain root 2 by pi, and if your duty cycle is varying, then your conversion gain will reduce. So, this is for passive mixer how the conversion gain will affect the duty cycle. So, what is the overall consideration, that we want to mimic the square in more towards the sine wave. So, let us say if we consider the T by 2 only the 50% duty cycle, then only the 2 points of the sine we are considering. If we try to have the more LO waveform and a 25% duty cycle, here you are considering the 1 point, another point, and so this is we are decomposing the more sinusoidal wave LO, considering the duty cycle 25% duty cycle. So, it can consist more points in the effective LO. So, current conversion gain is given by root 2 pi cos omega LO tau by 2, and maximum conversion gain is achieved when our tau is 0 or 25% duty cycle LO signal, and the we already discussed the simulation result, it is for 40 nanometer, and the simulation finding aligns closely with the analysis except for cases with less than 25% duty cycle, and during no overlap time the RF current source charges this capacitance almost linearly, and once any of switches are turned back on, this charge is delivered to the output and retrieve some of the signal loss. So, this is how we can consider the different duty cycle while considering the conversion gain. So, that is why we should have a preference given towards generating the 25% duty cycle, but preference will be given to the non overlapping clocks. So, how we can generate the non overlapping clock? So, on the right side we have a figure which will widely used to generate a non overlapping clock. So, if you have a LO signal, there is a divide by 2 counter divider, and that divider will generate the 4 phase, that is I bar. So, this is I bar, Q bar, and that is a 50% duty cycle. Now, what we are interested to generate a 25% duty cycle. So, in order to get the 25% duty cycle, so here this is a I, then there is a I bar, then Q. So, I and Q is the multiplied, and if I and Q is the multiplied, you will get a 25% duty cycle, and that will means that there is a AND gate is required, an inverter, you will generate the 25% duty cycle for LO1, and then LO2 and LO3 and LO4. So, how this is how you can generate the 25% duty cycle, but what is the disadvantage of this? Let us say if you are working at a 10 gigahertz, then you need a LO which is required at a 20 gigahertz. So, you require a 20 gigahertz LO which is divided into the 10 gigahertz here. Again, you also need very high speed and inverter that is also reduce the performance, or there is a possibility that sometimes after certain frequency you will not get a non overlapping 25 percentage duty cycle signal. So, that what is the effect? Ultimately it will reduce the your conversion gain. So, that is why overlapping LO signal introduces a crosstalks and degrade the mixer noise and linearity. So, methods, this is how the 25% duty cycle are generated, including the use of AND gate. You can also use a shift register, which is much better way, and it will has an advantage in terms of phase error and jitter. So, shift register approach is much better. However, this AND gate is also been used. So, if we want to manage this overlap, so choosing the size of inverter buffer that we are using to minimize the overlap and considering the process and temperature variation, and small no overlap periods are generally acceptable, and that delta V, this voltage is considered tau into Is by Cp. So, overlapping must be avoided to present the crosstalk and image issue. So, this is why we need to manage the overlap. So, there are 8 phase mixer. So, different phase mixer can be made to realize the more ideal LO, the sinusoidal LO. And what will happen that this will help us to reduce the amount of harmonics second order, third order, because we are going more towards the sinusoidal. If we consider the only square, then it has all the third, fifth, seventh, all the harmonics. But if we consider the 25% duty cycle multiple LO signal, then it will help us to reduce the amount of the third, fifth, seventh harmonics that is generated. So, we can have a 2 phase mixer where we require a 2 point sampling, the conversion gain is 2 by pi. Then there is a 4 phase mixer, that is a 4 point sampling, the conversion gain 2 root 2 by pi, and for 8 phase mixer 8 point sampling is used. So, employing an 8 phase LO in mixer design offers advantage in harmonic rejection, as I told, noise aliasing reduction, and immunity to harmonic blockers rejection of the harmonic up to 7th order. So, this is widely used in order to block the blockers also, and this also leads to a more fundamental gain and reducing the unwanted harmonic component in the mixer output. To generate the required 8 phase LO signal, the fundamental LO frequency is set at 4 times the LO frequency, and signal generation involves using a divide by 4 circuit along with AND gates. So, again your power consumption in LO generation is increasing, you are going to use the high frequency compared to what you require. So, that is one of the disadvantage of the circuitry. However, the advantage is there is always a trade off that it can reduce the, it is immunity to blockers, it will have a rejection of the harmonics. So, that are the advantage the considering of the 1 by f noise. So, this all problem can be solved, but we can have a higher power consumption on the LO side. So, based on this, there is a possibility of making a mixer which is called the M phase mixers. So, we can represent the Fourier series representation for each of the LO signal driving the branch, that is given by SKT sigma n raised to minus infinity to infinity a n e raised to minus j n 2 pi by m. So, where m is any phase that we are interested, and we can decompose this into LO1, LO2 to LOM, and that is a cos 2 pi into 0 by m, cos 2 pi into 1 by m, and then it will go on. And finally, we need to add, we are doing the summation. There we are adding by just connecting. So, that is current is added. Here Sk is effective LO switching the kth branch K1 to M, and that An is given by using the sinc function, that is e raised to j k n 2 pi by m into sinc n by m. So, there here n can be 0, 1, 2, 3 whatever is the number. Now, means LO1, LO2, LO3 and up to LOM. So, it is obvious that the effective LO signals are identical, but shifted only by T by M with respect to each other. Now, at net effective LO ST consists of the effective LO signals of each branch scaled by a cos k minus 1 2 pi by m and added together. So, your ST we can write it down, which is sigma k is equal to 1 to m cos k minus 1 2 pi by m into SKT. We can get sigma n is equal to minus n infinity to infinity a n e raised to j n 2 pi by m e raised to j n WLOT into sigma k is equal to 0 m minus 1 cos k 2 pi by m into SKT. So, for the main harmonic, then n is equal to 1, the effective LO for the say output V1 becomes k is equal to 0 to m minus 1 cos k 2 pi by m e raised to this equal to m by 2, and this is your final output, which is a combination of sinc and cosine function. So, what is the implication of increasing the number of phases in a mixer design? So, if we try to increase the number of phases m, then the LO amplitude, effective LO amplitude will go towards the ideal 0. So, as the number of phase m in the mixer design approaches to infinity, the effective LO signal closely approximate an ideal cosine waveform. So, that is what we desire. We can reduce all the harmonics and we can get the ideal cosine waveform. And despite the switches being driven by a square wave signals, the effective LO amplitude approaches a unity, resulting in a minimal harmonic down conversion. And while large m values require more complex clock generation, it is much obvious. That is why here there is a one graph is plotted for number of phases m with respective to effective LO amplitude. So, if you consider m is equal to 2, it will have a minus 4, then if m is equal to 4, that is around minus 1 dB, and if you consider 8, it is around 0.97. So, 8 pi pi into sine into pi by 8, which is around 0.97, and that will approximately 1. So, we do not need to go for higher m phases, because it will increase the power consumption, and we can also get the performance as a ideal cosine wave, that is with amplitude of 0.97 So, mostly m is equal to 8 can be considered, and for 4 phase mixer are more popular choice for narrowband receiver due to the complexity and allow generation overhead for high values of m. So, finally, this point is widely used, that is a m is equal to 4, which will help us to design the 4 phase mixer. So, that has a non overlapping clock, 25% duty cycle with a 4 phase instead of a 8 phase, and that will have a consideration of removing the uh, harmonics and improving the blocking performance. So, we will discuss more about this mixers in the next class, and then we will try to conclude the mixer design. We will then start discussing about the oscillators. Thank you.